Hello, Jeremy.
Hello.
Hello, Pooran. Christian is online today. Should we wait for others? Curtis is always there, right? So we should give it a minute. Maybe. How are things? Good. Yeah, I think let's begin with homework for you Monday. And midterm 2 is on 26th of March. We introduced the idea of a electric current carrying wire, a small loop in the far field approximation, but we can actually change the story a little. So and call first let me so magnetic or point magnetic. Did I introduce the idea of point magnetic moment? I'll do that today anyway. So point magnetic dipole moment. Right. So the idea is we have a circular loop of wire that we talked about, and it has a radius of A, and the observation point could be anywhere out in space. So let's say R, position R, and the far field approximation we said is the case when A is very much less than R, and we got an exact expression for this. But let's take the extreme scenario where A tends to 0. A is pretty much going in the limit A tends to 0, and then you would say, oh, that's almost meaningless. This is actually then the current loop doesn't exist at all, it goes to 0. But for that case, we actually don't set A equal to 0. Instead, let's say A square is 0. There's a difference between A going to 0 and A square going to 0. It talks about how fast we are setting something to 0. That means the area of this loop is going to 0. But then we'll say that the current in the loop, so that's I, we take it to infinity. So current is very large, area is very small, but in such a way that the product of these quantities remains fixed. A very large quantity, before we actually take the limit, we first, if we do this, then they cancel out, and that remains fixed. And that will be called a point magnetic dipole moment. Remember, if you have a point magnetic dipole moment, M is equal to, for a wire, this is I, times the area, which is pi a square. Like if you remember your introductory level physics, if you have a current carrying loop of wire, current I in it, and the area of it, that's your magnetic dipole moment. But we also need an A direction to it. The direction is you use your right hand to curl your current, and the area will be the thumb. So right hand rule gives you the direction of that, and let's say that's your direction and hand. But if it is in the extreme limit, when this actually goes to 0, then we don't have to talk about I, we don't have to talk about a square, we simply say this is M and half. So this is just M. It doesn't have to be, we don't have to talk about what is causing that current or area, because one is 0, one is infinity. There's a product that is unique, and that is circular. And for a point dipole moment, so M, we have shown that the vector potential now would be vector potential due to this is equal to mu naught over 4 pi times the vector M crossed with R over R cube. Right, that's what we have shown in the last class. We also can actually now calculate the magnetic field, right? So once we have the vector potential, and by the way, what is the direction of this vector potential? We should point out. Like typically, vector potential is in the direction of the current. That's a typical thing if everything is steady, but you can, it need not be always the case, especially if there's a superposition of two loops, then you can have complicated structures. But in simplistic scenarios, where there is only one direction of current, a unique one, then it's in the direction of the current. And you will notice what is M if M was in the direction of Z, and R hat was in the direction of, say, let's say it's in the plane of the board, and then Z cross R hat, so let's say this is M, right? So M cross R hat will be going into the board, which is also the direction of, that's your, if I were to draw a tangent there, so that's your phi hat. So the observation cylindrical coordinate phi hat, and that's the direction of A. So A, if you have a magnetic dipole moment, which is basically a magnet. So, so maybe I should point this down here. A magnet, a bar magnet, let's say, is best represented by a point dipole or magnetic dipole moment. I don't have to say it is a point magnetic dipole moment. So it is just a magnetic dipole moment. That's a classic example. So all the experiences we have of magnets should be explained, should be able to try to explain this using the potential given as M cross R cube, but then magnetic field is what we usually use. So we should be able to get an expression for that. So let's go ahead and calculate the curl of this quantity, which we sort of did last time. So let's calculate that. So the magnetic field is equal to the curl of A, which is equal to the curl of M crossed with R over R cubed. And I'll pull out the mu naught over 4 pi. I can use the triple what do you call the back cab rule to do this, but just I have to be careful that this is a gradient operator. The gradient operator also distributes, the back cab also has this distribution property. But M is a constant, it doesn't change with position. So that is a simplicity in here. And that's equal to mu naught over 4 pi times M, and the divergence are over R cubed. That's your 3 vectors. The center one is M. That's the one of the vectors. And the second one is in the direction of R, but then I have to act this gradient still on that. So this is equal to the directional derivative, if you want, of R over R cubed. We very quickly sketched on this in the last class, but be careful that we were not careful with the units there. I was just sketching it at the end of the lecture. Oh, here also there should be mu naught over 4. So what is the divergence of R? What will this be equal to? Like, notice that whenever you see R over R cubed, what does it remind you of?
Electric field.
Electric field due to a point charge. Right? So electric field due to a point charge, what is the divergence of the electric field due to a point charge? Using the Maxwell's first equation, it should give you the charge density, right? Which is nothing but a delta function, right? A point charge exists only at one point, so it's just one delta function there, and that survives in there. So that's equal to mu naught over 4 pi times M times 4 pi times delta function, where this is the position of the charge itself, but since it is R over R cubed, this is not translated, so it is right at the origin itself. So that's all. And this is what we did not emphasize on last time, since I was sketching this very quickly, I didn't point that out. But today, since we're doing this carefully, so this is equal to the point term. So that's your first term. Second term, similarly, is equal to minus mu naught over 4 pi M dotted with. So let's apply this to both. We have done this in the last semester a few times. This can either hit the numerator or the denominator. When it hits the numerator, I use the property that the gradient of the position vector, this is, notice that there's no operation, it's a dyadic in there, so it's an outer product if you want, and that's 1. So you get 1, the unit dyadic over R cubed, that's the numerator. When it acts on the numerator, when it acts on the denominator, I get a minus 3, right? Minus 3 over R raised to 4, and I also use the fact that gradient of the magnitude of the R is just R hat, and I can write this as 3 R hat over R cubed. If you're not sure how you get that, do review your vector calculus from last semester. We will use this again and again often. I can take the dot product right away there. So this is equal to the 4 pi cancels out, mu naught times M times the delta function, which is not really relevant, right? Because we're talking about the magnetic field, and this magnetic field exists only at one point. right at the position of the magnetic dipole, it is there, and otherwise it doesn't. But we are going to keep this because we want to check whether the divergence of the magnetic field is 0 or not, and that's the reason why we're keeping it. For all experimental purposes, or if for all application purposes, this is never going to contribute. Right? So this is more for consistency, that everything is working out well mathematically. So going ahead, and let me take the magnetic minus sign in, and this is equal to plus mu naught over 4 pi, and let me pull the 1 over r cube, and this is 3 times that, and minus m. And this is a classic distribution of a dipole. How does this look like? It looks like what a magnetic field of a magnet looks like, right? So this is how the magnetic field of a dipole looks like. And the direction of M itself is right along the symmetry line of that. So that's your M. That's your magnetic field lines. And in your homework, you have to actually calculate the magnetic field along the axis. So at a few different points, I ask you to actually explicitly calculate this point. We have done this before. If you get in trouble, what exactly it is, you should go back and do the electric dipole. There were similar homeworks back in the first semester, and it's pretty much repetition, except that earlier we used to have P there, and now it is M. So it's very similar. So keep this delta function in mind, and let us do some small verifications. So notice that there is an important statement in one of the Maxwell's equation, and that is that the divergence of the magnetic field is equal to 0. That is the importance is that states that there are no north poles and no south poles. Like you can never break apart a north pole from the bar magnet, right? It can never be separated out. But if that is true, and whatever magnetic field we just now generated using a bar magnet, that should satisfy this. And let's see mathematically if that works or not. And that is a reason why the delta function there, even though it exists only at one point, that is crucial. Right? So let's check this out. So whatever expression we had, let's substitute this in. Right? Well, let's start with the left hand side. So that's mu naught times m times there is a delta function, and then we have plus mu naught over 4 pi times 1 over r cube which one should I use? Let me not exactly use the last expression. I go to a slightly previous expression, which is minus, this comes out, this stuff here, right? So this is minus mu naught over m. If you go a few steps back, this also shows up in this form. Okay. And the claim is that this is equal to 0. We want to check that this is actually indeed equal to 0. So what we do is, first one is a derivative of a delta function, a very complicated object. Right? So we keep it intact, right? We don't want to play with that. Instead, we expect that it will get cancelled, right? So it is mu naught. This is constant. It doesn't depend on position. So this is m, so it becomes a directional derivative of the delta function. Okay. And then the second term, this is the divergence of whatever is the free vector there, which is r. But this divergence can go through the constant magnetic dipole because that doesn't depend on the position. That's a property of the point dipole. It also commutes with the other gradient, so it goes through n. And what we have is minus mu naught over 4 pi m to the gradient. But this gradient operator acts on that free vector, which is this. Which is nice because we already said that that's the electric field due to a point charge. So the divergence of that will be a delta function. So again, there will be exactly same thing coming up, right, with the opposite sign. So we don't have to really evaluate this derivative of delta functions, but we do see the same structure coming in. And that's delta function. So they do cancel exactly, and that's equal to 0. Which is necessary because if by any chance it's not 0, then we're saying that, oh, it's possible to have magnetic dipoles. There is also one more thing we should verify while we are in doing all this. Remember that magnetostatics involves a few things. First is magnetostatics involves the divergence of magnetic field is 0. That's one of the Maxwell's equation in static magnetostatics. The second is that del cross B is equal to mu naught times J. And the third was this implies that B is equal to del cross A. And the second equation implies that if you want del dotted with J is equal to 0. Oh, that is fine. Oh, there was one more equation in all this. This is true only in the Lorentz gauge. Right? So there was a gauge. So we should just make sure that that is also satisfied. So let's very quickly calculate the divergence of the vector potential for a point magnetic dipole. Right? That's our expression, which is in the circular directions. So this is mu naught over 4 pi L dotted with m crossed with r over r cubed. Instead of doing the actual evaluation, there is a simplicity you can use. Use the property that the electric field can be written in terms of an electric potential. So what we have is del dotted with m and then crossed with another gradient operator of 1 over r with the minus sign if you want. That's because gradient of 1 over r is the electric field. But that has to be equal to 0 because now there are two gradient operators coming and there is a curl in this, right? There is an epsilon ijk that is sitting in this, and that will be equal to 0 because this is one is anti-symmetric and one is symmetric, so that will always be 0. Again, at a very general level, we don't have to really go into specifics. It will always be true. So that's some of the properties of a point magnetic dipole. But there is one thing that we can do now. What is first of all the point or what is a magnetic dipole moment as just as an understanding of a point charge? So let me talk a little bit about that. So this is a point. Again, magnetic dipole moment. Magnetic dipole moment. So let's think of a single point charge going in a circle. So this is not actually current carrying wire, so let me show that by the dotted lines. Right? But there is a point charge Q that has a velocity V, instantaneous velocity V, but its speed is the same, so it keeps going in a circle, right? And one would say that if that is the case, if a charge is going in a circle, then that might correspond to a current, right? Especially if it starts going very fast, especially to our eyes, it will seem like there is a current in that circle, right? So what will that current be? So let's think of our magnetic dipole moment M as maybe, right? So let's see, M, just as a magnitude, this will be equal to current times the area. That's a definition of the magnetic field. Current times the area of the loop. So here, there is no current, but we are talking about a charge that's going in circles. So that's your radius A. That's your radius A. And current, we would say, is Q over the time it takes to or how much charge goes through a point in a unit time, right? That's your current. But how much time does it take? How many charges go through this point? It is the same charge it is going, but in every time period t it goes through, right? So that's time period t. Who knows? It's the same a charge that is going on. It doesn't matter in our definition. So let's move this around a little. We want to introduce velocity, right? If it is a circular motion and if it is uniform circular motion, that's the same as 2 pi a over the time period, right? That's the distance it travels. And I multiplied by a 2 and divided by a 2, so that the circumference divided by the time period gives me the speed of the charge. So that's velocity v. And let's say this is a. Actually, let me change this to r. Just so that it doesn't matter actually, it's very irrelevant, but it might give you more, since you see expressions with position r, it might give you more insight. That's velocity v. So let me write this as q over 2 times, let me write r first, and then velocity v. Let me write the velocity v a little further, that I introduce something there. I multiply by nm and divide by nm there, and we see that there is an r times mv. What is r times mv as far as dimensions go?
Angular momentum.
It is angular momentum, very good. So that means the magnetic dipole moment seems to have the information about angular moment, and angular momentum is in the right direction also, it is coming out of the circle. So in general, what happens is that for a point charge, so this is for something going in a circle, in general, m, the magnetic dipole moment as a vector quantity, is q over 2m times r cross mv, which is momentum, which is equal to q over 2m times the angular momentum L. Which means that whenever something is going along an orbit around something else, it will act like a magnet. If there's a charge going around an atom, that means it is acting like a magnet. So it has a magnetic dipole moment. So you will see a magnetic field associated with that, because effectively there is a current I in there. And in that sense, most of the atoms have magnetic dipole moments associated with it. Unless they are in the S shell, then it is spherically symmetric. Then this they also need to be in a plane, right? That's not very well defined, and then they cancel out in a sense. So let's do the following. Let's have actually a a circular ring. So let's have a circular ring which is having a total charge Q on it. So this is all positively charged. So we talked about one charge going in a circle. Now let me have a ring and let me make it go the whole ring. Let me rotate that whole ring. And that means I have to say how much I rotate, right? Once it's time period of rotation, or I can say angular frequency, right? Angular frequency, remember, is Q pi over time period t. So I can say, I can specify the angular frequency with which I'm rotating. And this whole thing is now effectively each charge is contributing to a current, and we can say what will this magnetic dipole moment be? And then the question comes, oh, how do I calculate the magnetic dipole moment? So let me go back to this expression that we talked about in a moment ago. So let me go back and erase this part. And that was to introduce the idea that there is angular momentum. Get rid of your m order, so that was just multiplied to get the angular momentum idea. And let me write this as half times r crossed with q times v. That has this feature that q times v is nothing but the current associated with a point charge. But now let me think of it as a density, right? If I want to think of it as a density, I would say this is 1 by 2 times d cube r, or let me, so I multiply by a small volume element d cube r, and then divide out by that same volume, right? So that's 1 by 2 times r crossed with, this is a current per unit volume, I will call that J. That's what we have been calling current density J of R. So if I have a lot of current densities, what I do is I just have to integrate that whole region, scan for any currents, integrate over the whole space, and I get the total magnetic moment. So whenever I have a current, I can get a magnetic dipole moment using that. So now I have the following situation where I'm having a charge and rotating this, and then we are talking about, oh, how do I get a current from my rotation, right? So remember again, there was this velocity v here. How is velocity and angular velocity related? So remember, angular velocity is coming out of the board, right? So there is position r, this is the radial vector, velocity is tangential, and omega is actually coming out of the board, and you will notice that velocity v is equal to omega crossed with r. We typically, in at least early stages, we don't worry about the vector nature. We simply say this is v is equal to omega r. That's how we introduce this. The velocities, we already use this. Velocity is 2 pi r over t time period. But a more, if you want to keep the directions intact, you would say this is velocity is equal to the cross product of the angular frequency times r. So what will be your current density then? So if it is q times v, so that is q times omega cross r. That's what you want to do. And the current density would be just dqr, and you want to multiply that. So let's try to see what is the magnetic dipole moment associated with that. So if if you have a charge density Q rho of R, if you have a charge density for this circle would be equal to, there is a total charge Q, and I think this was raised by uh, uh, Jeremy, right? He was curious about how do we get this coefficient. So let me elaborate this here. I don't know what's the coefficient. For sure, there is some constant C, and I have a delta function at Z, and there is a delta function at radius A, right? A or R, let's say. So this is rho minus A. But I do know that the total charge for this is equal to Q. So that should give me an idea to calculate C. So I do the total volume. So this is dqr of rho has to be equal to Q. So I evaluate this. This is integral of dz. This is rho d rho and d phi. 0 to 2 pi, 0 to infinity, and minus infinity to plus infinity. All this times C, we say, is cannot depend on any coordinates. So this is, if you want to pull it out, that's what we want to find out. And that's delta of Z times delta of rho minus A. The integral on Z is trivial. Rho gets replaced by A everywhere. So that's C times rho gets replaced by A, and there is an integral of 0 to 2 pi remaining. But that's simply 2 pi A. So C times 2 pi A is equal to Q. That means C has to be equal to Q over 2 pi A. So our charge density, so this implies that C is equal to Q over 2 pi A. So that implies this is Q over 2 pi A times delta of Z times delta of rho minus A. So if I go to the other side of the board, oops. So what we are talking about is that there is a charged circular ring, and it is rotating with angular velocity omega. First of all, this is total charge Q. So the charge density for this is equal to Q times Q over 2 pi A times delta of Z times delta of rho minus A. And that should be straightforward. Then we ask, what is the charge? What is the current density? It has a current density because it's rotating. And what we do is, to get the current density, is multiply the charge density with velocity at every point. Right? So that's what we typically do. But velocity is omega crossed with R. Times of R. That's how you would calculate. That and omega is given to us, R is the unit vector. So now that's your charge current density for this ring because of its rotational motion. That's your charge density, but the question could be, what is the magnetic dipole moment for this ring? We are not actually literally having a current, we are actually having a charge distribution and making it rotate. So what is its magnetic dipole moment? We said magnetic dipole moment is half of integral over all space, scan basically for wherever the current density is, times R crossed with J. But, so notice there's a three-step problem, right? J is coming because of the rotation and because the charge density is there. So first get the charge density, that because of the rotation leads to a current density, and current density leads to a magnetic dipole moment, and we can do this integral now. This is half of integral over all space again, and R crossed with omega crossed with r times rho, right? That's it, which is 2 pi a, or q over 2 pi a times delta of z times delta of rho minus a. Omega is, we can choose this to be in the z direction. So omega could be in the z direction. Then omega r crossed with omega crossed with r will be equal to omega times r square times minus of omega dotted with r times vector r. But everywhere where this circle exists, omega dotted with r is 0. Like at this stage it is not, but inside the integral it is, because this makes it stay on the plane of the board, and this makes it omega times r squared. So what we have is it's in the direction of z. So I can bring out the omega. So it's 1 by 2. Let me do this, minus infinity to plus infinity dz. We have 0 to infinity rho d rho, 0 to 2 pi d phi. And we have omega times r squared, q over 2 pi a, delta of z times delta of rho minus z. Hopefully on the board still. Oh, I'm off the, okay. Evaluate the integrals. Notice that these are all constant. Omega is a constant vector. Q over 2 pi is constant vector. So that's omega. So apparently the direction of the magnetic moment is in the direction of omega, which is because of the rotational motion. That's clear. 1 by 2 times q over 2 pi a. The z integral is gone, and the rho integral replaces rho with a. That's a that's coming out from here, this rho, and and the r also, right? Where is r? R is everywhere on the ring. So everywhere on the ring, wherever z is equal to 0, r is basically equal to a squared. Right? So this is rho is a, and r is actually equal to, so in terms of how do you put this? So we can say, so this is r. Yeah, maybe I should do one more step here, right? Let me not jump a step, because this is in mixed coordinates. R is spherical coordinate, rho is actually cylindrical coordinate. Let me not confuse there. So rewrite this, even though sort of it is trivial. Rho d rho 0 to 2 pi d phi, and let me say this is omega times q over 2 pi a, and that is r square, which is nothing but rho square plus z square. The spherical coordinate and cylindrical coordinate are related by, so this is your vector r, that's your rho, that's your z, that's your z, that's your rho. And if you want, that's your angle theta. So that's r square is rho square plus z square, and then you put a delta of z times delta of rho minus z. Then we know that, oh, the z term doesn't contribute. So that's what I was trying to put, that r equal to rho right away. So that's equal to vector omega times q over 2 pi a times 1 over 2, z integral goes away, rho gets replaced with a, but then there are 3 of them, right? This goes away because it's 0. 3 of them, and that's a cubed. And rho gets replaced with a. Now let's see. a cube and and 2 pi, right? And that is 0 to 2 pi d phi. That's all, I suppose. So this is equal to omega times q. Notice this has this dimension of 1 over time, right? Omega is radians per second, so that gives you the dimension of current, and one of the so this is 1 over 4 pi, and that is an a squared, and this is 2 pi. So all of them cancel out. And if you want, this is omega times q a squared over 2, I suppose, right? Is this correct? Did I miss something? I think it is okay. Yeah. A simple thing you could do, extend this to, is that what if there was a sphere, it was charged. So let's say this is, so what if you have a sphere of radius a with a total charge q, and again make it rotate around its axis now, so that's with omega here. And again, you can do the same analysis. We know how to write the charge density for a sphere. There's an omega cross r that leads to a current density, and then integrate the current density to get the magnetic dipole moment, and it comes with a very similar answer, except that this number will change there. But I won't do that here. And your homework has a similar problem, probably identical to this, I think, something like that. So I'll let you guys explore that. That's all. I'll stop here. Any comments or questions? Okay. Have a good weekend.
Thank you, you too.
Yeah.
I will talk to you on, or I'll send you an email, probably with my slides before Monday, and then I can go through the presentation with you then after class. That's
Sure. Yeah.
okay. All right. Thank you.